Now let's talk about the second law, efficiency. Now a common measure on the energy use is the first law efficiency, which is denoted by the symbol eta 1, where 1 means that we're talking to the, or we are referring to the first law of thermodynamics. And the first law efficiency is nothing but the ratio of the output energy from a device upon the input energy to the device. Okay, so this means that this is how you can mathematically express the value of the first law of, or the first law efficiency. Now the first law is concerned only with the quantities of energy and disregards the form in which the energy exists. So the if you have to write it down in a nutshell, so first law is concerned only with the quantity of energy. It is not at all bothered about the quality of the energy, or you can say it disregards the forms in which the energy exists. So I will just write down that it disregards the quality of energy. Alright, so this is how you can define the first law efficiency. Now it does not also discriminate between the energies which are available at different temperatures. Now the energies as a function of temperature means we are talking about the quality. So it is one and the same thing. That is the second point, that it disregards the quality of energy as well. Right, so it is the second law of thermodynamics which provides a means of assigning a quality index to the energy. Right, so the concept of available energy provides a useful measure of the energy quality. So that is what we have been doing in these video series. Now, so this gives rise to a second law efficiency. So second law, it deals with the quality of energy. Okay, which means that the amount of energy varies upon the variation of the temperature at which it is available. Right, so let us define the second law efficiency, which is denoted by eta 2. Now with the concept of second law, it is possible to analyze means of minimizing the consumption of available energy to perform a given process, thereby ensuring the most efficient possible conversion of energy for the required task. Now if we have to define the second law efficiency, then we can say that the second law efficiency of a process is defined as the ratio of the minimum available energy. Let's write down the minimum available energy. It is also known as Exergy. Okay, so it is the ratio of the minimum available energy which must be consumed to do a task divided by the actual amount of available energy consumed to perform a task. So divide by the actual available energy which is required to perform a task. Okay, so if you can minimize the Exergy requirements to perform a task or to perform a process, then you can increase your second law efficiency, and you can also ensure the most efficient possible conversion of energy. Alright, so taking this forward, this can be written as, let us denote the available energy by a letter capital A. So minimum available energy upon the actual available energy. So this is how you can denote the value for a second law efficiency. Right, now let us say a power plant converts a fraction of available energy Okay, and I can also say that this available energy, okay, so this available energy is also equal to the maximum work output. Alright, so what a power plant is doing, it is converting a fraction of this available energy or this maximum work to useful work. Alright, so let us say that for a desired output of work, so let us say a desired output of work which is W. Now this is corresponding to the minimum available energy requirement, and the available energy that we have, this is corresponding to the maximum work output. Okay, and we also know that the irreversibility is equal to the difference between the maximum work divided by the actual work that is done by the system. So if you substitute these values in the mathematical equation for the second law efficiency, you can say that eta 2 is equal to W upon W max. Alright, so this is how you can denote eta 2. Now let's write down the value of eta 1 as well. So eta 1 is equal to the output, that is W upon heat input, which is Q1, let's say. Okay, so this is the value of eta 1. Now let us manipulate algebraically this particular value. Okay, so let's write down the value of eta 2 again. So eta, not eta 2 but eta 1. Let's write down the value for eta 1, which is W upon Q1. Okay, let's multiply and divide this by W max. Alright, so upon doing so, you can combine this and this, and you can combine this and this. So you would have W upon W max into W max upon heat input. Alright, so one thing that you should always know, that the maximum work output for a given heat input, it corresponds to a Carnot cycle. Okay, so this expression gives the value of the efficiency of a Carnot cycle. Alright, so I can rewrite the equation as eta 1 is equal to, now this is eta 2 into eta Carnot. So this is how you can relate the first law efficiency, the second law efficiency, and the Carnot cycle efficiency. Okay, you can also rewrite it that eta 2 is equal to eta 1 upon eta Carnot. Okay, so this is how you can relate these two values. Now, if you remember an equation, and if you remember the expression for W max from one of the previous videos, so W max, this can be written as Q1 into 1 minus T naught upon T, isn't it? So this is the value for W max. And when you use this particular expression, okay, and when you put this value, so you have eta 2 as W upon W max. So when you put that value of W max over here, okay, so let's see what you get. So you get equal to W upon Q1 into 1 minus T naught upon T. So this is what you get, isn't it? So when you combine it again, so you get W upon Q1 as one value into 1 upon 1 minus T naught upon T as the other value. Now if you look at this term, this is nothing but eta 1 and this is nothing but the Carnot efficiency. Alright, so this is 1 upon Carnot efficiency. So this becomes eta 2 is equal to eta 1 upon eta Carnot. So the above expression, this expression can also be derived if you remember this formula and you substitute it in this particular formula. Okay. Now let's assume a case. Let's assume a case where we have some solar energy. So we have some solar energy. All right. And this solar energy, let us say QR. All right. This is available at a reservoir storage temperature TR. So this is available at temperature TR. And you have another quantity QA. Okay. Now this is the quantity of heat which is transferred by the solar collector. So this is the heat which is transferred by the solar collector. Now this solar collector is at temperature TA. Alright, so then if you talk about the first law efficiency, so first law efficiency is equal to QA upon QR. So this means that the heat is available at this particular in this particular quantity and at this temperature, but the heat that you're getting is of quantity QA and the temperature is TA, so the values are different. Alright, so this is the actual heat delivered and this is the maximum heat that is available, right? So, and if you write down the value of the second law efficiency, that is eta 2. Now this is the ratio between the Exergy output or the available energy output upon the Exergy input. All right. Now this means the available work or the the actual useful work that is done. So it is equal to QA into 1 minus T naught upon TA. So this is the value of, you can say, W or the minimum available energy upon the Exergy input is equal to QR into 1 minus T naught upon TR. So this is one expression that should be noted down for eta 1 and eta 2 where we deal with solar energy. Okay, and when you look at this particular ratio, so this is nothing but eta 1. Alright, so I can say that eta 2 is equal to eta 1, okay, into 1 minus T naught upon TA upon 1 minus T naught upon TR. Okay, so this is how the first law and the second law efficiencies are related. Alright. So this was a video on the topic of the second law efficiency. Alright. So now in the next video, and before we talk about the illustrations of the second law efficiency, let's talk about the Exergy balance, and we'll talk about the Exergy balance in closed system and Exergy balance in a steady flow system.